Okay, so if you're ready, I think we can start. Our next speaker is Olena Karlova with a talk about Rolewicz theorem on inversion of continuous bijection between f-spaces.
Yes, thank you very much for introducing me. And of course, I would like to thank the organizers for inviting me. And actually, this is my first time on this conference. It is rather strange, but it is so. So thank you very much again. So I will speak about an old result of Rolewicz. About the inverse function of continuous bijection between f spaces. Well, I'll start with some historical remarks and motivation of this work. So by f space, we understand the classical definition, namely this is a vector space which is which admits a translation invariant metric such that with this metric the space X is complete. And well-known theorem of Stefan Banach tells us that if we have two f spaces, then if f is only additive and continuous bijection, then the inverse mapping is also continuous. And the next example shows that if we have no the next example shows that in general the inverse mapping can be discontinuous not only in one point but in everywhere dense subset. But I see that I have a graphical mistake. So let me have two countable products of f spaces x and y, where every xn and yn are f spaces, and consider for every n a continuous bijection between xn and yn such that by d of fn minus 1 we denote the discontinuity point set of the inverse map. So each of these bijections has only one point of discontinuities. And we define a function f as the following. And this function is continuous bijection, but the inverse is not everywhere dense. The discontinuity point set is of this inverse map is everywhere dense in y, not in x. I'm sorry for this small mistake in accuracy. So the inverse map can be discontinuous, widely discontinuous. And Stanislav Mazur asked if an inverse mapping of a continuous bijection between f spaces belongs to the first Baire class or something like this, which class of inverse mappings form the collection of continuous bijections between f spaces. Let me recall that the function belongs to the first Baire class if it is a pointwise limit of a sequence of continuous functions. And in his article on 1958, Rolewicz proved that if x and y are f spaces and x is separable and locally compact, then the inverse of every continuous bijection is Baire one, namely pointwise limit of continuous functions. And there are some questions which naturally arise from this result. So the first one is, how can we generalize this result how can we extend this result in the following directions. First one is, can we somehow avoid this property, this condition of X and Y to be F spaces, for example, not linear or not complete. And also the second one is a condition of separability and locally compactness. And the third direction is to see if this result true. I mean, when the inverse mapping is not necessarily bare one, but another class, for example, more wide classes of functions between continuous and bare one. So the main result of my talk concerns actually the proof. This concerns these three steps of the proof of Rolewicz. So I will briefly speak about his proof. The proof consists of three steps. The first step is to show that image, the following fact is known, but the image of an open set is of sigma for every continuous bijection, and this fact follows that the inverse map is of the first Borel class. The second step is to prove that every Borel one mapping between F spaces or between metric spaces is a uniform limit of a sequence of bare one functions. And the third step, the final step, is to show that uniform limit of bare one functions, so that the class of bare one functions is closed under uniform limits. And these three steps together give us the result of Rolewicz. What I can say about the first step about continuous images of open sets. The result is the following. It's not hard to prove that if we have a locally compact metrizable separable space and Y is a topological space, then for every continuous bijection, we have the following fact that the image of open set is simultaneously F sigma and G delta in space Y. This gives us that the inverse map is not only Borel one, but we call such maps G delta measurable. For example, every continuous map is G delta measurable, and every G delta measurable map is Borel one with between respectively good spaces, for example, metrizable spaces. If we consider if we would like to omit some conditions on X, we will see that each of them is necessary for this result. And the first simple example, if X is a locally compact metric space which is not separable, so the previous theorem is not true, because we can consider, for example, a real line with a discrete topology and take an arbitrary non-Borel set. In the Euclidean topology, which is evidently open in the discrete topology, then the identity map is continuous bijection, but the image of this open set in the discrete topology is non-Borel. So the condition of separability is necessary in the result of continuous images of open sets. The second example shows that in not locally compact space X, if X is not locally compact, then this the previous result is also not true. And there is an example of two complete, namely Polish spaces, complete metric separable spaces, and to power n and 0, 1. And we define such a continuous bijection by the rule. We have a sequence from n to power n, n1, n2, and so on. And in the right side, we consider such a binary representation. We consider n1 of ones, then 0, then again ones, but with an amount of n2, 0, and so on. This is a binary representation of a number between 0 and 1. And if we consider such an open set of the product n to power n, so all such sequence where sum of nk is even, then the set is open, but we can prove that the image is not a G delta set. And the third, when we consider not a bijection, but simply continuous function, so we may consider simply a projection, for example, from R2 to R, a projection to the first factor, and take a Borel set. It is well known that there exists a Borel set in the plane such that the projection is not Borel, but the problem is for us now that this set is not open, but we can use a result of Ketcheris. The result is following. We can make this set open in some topology, in some Polish topology, and the result is the following. If we have a countable family of Borel subsets of some Polish space, then we may introduce a Polish topology which contains the topology T with the same Borel sigma algebra such that every B is closed and open in this new topology. And in this new topology on R2, the set B is open, but this image of continuous but not a bijection function is not a Borel set. So all three conditions on X and on function F are, we cannot omit these conditions. The second step is to construct a uniform limit of a sequence of Bayer-1 functions, which approximates any Borel-1 mapping. I give here I try to give here a more general result, but there are a lot of results in this direction. But maybe in Kuratowski monography you can find proof of similar results, but the most general is the following. If we have a perfectly normal space and Y is a metrizable separable path connected space, then we can approximate every Borel-1 function with a uniform limit of Bayer-1 functions. And now in his paper, Rolewicz actually proved that the uniform that the Bayer-1, the class of Bayer-1 functions is closed under uniform limits, and he proved it using the next property, which he did not consider separately, but actually he considered such a property of space, which you can see. This property means that in space X, in metric space X, every ball is a retract of this space, and this retraction is continuous with respect to the center of this ball, to the second variable. Y is the center of this ball, so the ball with radius epsilon with center in the point Y is a retract of the whole space, and this retraction is continuous with respect to Y, to the center. And due to Rolewicz, we will call such spaces Rolewicz spaces or R spaces briefly. And so he proved for Polish spaces the next result, which I generalized, but essentially it was a proof of Rolewicz. If we have a topological space, then and Y be a Rolewicz space, then the class of Bayer-1 functions between X and Y is closed under uniform limits. Some examples of R spaces, there are all convex subsets of normed space. F spaces are Rolewicz spaces. Every metrizable zero-dimensional space is Rolewicz. And a more specific example, a unit sphere is a Rolewicz space, but at the same time, for example, an ellipse in R2 is not a Rolewicz space. So we need to find some slight modification of definition of Rolewicz spaces in order such nice figure as ellipse be a Rolewicz space. And we introduced the property of weak Rolewicz spaces. It is almost the same, but a weaker property if we have a constant C and the sequence which tends to 0, and the sequence of such retractions such that the ball with radius epsilon n is a retract of the space, but not the retract, but so it has a property of fixed point, but all other points we can map into the ball with a bigger radius. And this map is also continuous with gently continuous. And in this definition, ellipse in R2 is a weak Rolewicz space. And we can prove that this condition also is sufficient for the class of Bayer-1 functions to be closed under uniform limits. And another result concerning uniform limits of Bayer-1 functions was proved jointly with my colleague Volodymyr Mikhailuk. We proved that the class of Bayer-1 functions is closed under uniform limits, but Y is satisfies path connectedness and locally path connectedness property. So naturally it arises. It's easy to see that every path connected weak Rolewicz space is locally path connected. And naturally arises a question which I asked in the end of my presentation. So the main result is the following. If we have a metrizable connected and locally path connected K-sigma space, this means by K-sigma space we understand space which is a union of a sequence of compact subspaces. And Y be a perfectly normal space, then every continuous bijection has the inverse mapping, which is Bayer-1. And moreover, we may prove that if X is a sigma absolute extensor and space Y is, for example, a complete metric space, then the inverse map belongs to the first stable Bayer class. It is sigma continuous and belongs to the first stable Bayer class. That means that we have a sequence of continuous functions which stabilizes on for sufficiently large n. And questions which are natural and open, maybe they're not difficult, but for me they are open for today. The first question, if we have, this question is tightly connected with the problem of uniform limits of Bayer-1 class, with functions of Bayer-1 class. And if we have a metrizable path-connected and locally path-connected space, does there exist a metric, equivalent metric, such that XD is Rolewicz space or weak Rolewicz space? And the second question is also natural. If we have a Rolewicz path-connected K-sigma space, and Y, for example, be a complete metric space, does the inverse mapping of continuous bijection belongs to the stable Bayer-1 class? And the second question follows from this main result, where in order the inverse map belongs to the first stable Bayer class, we need that X is a sigma absolute extensor, such a strong condition. And I wonder if we can replace this condition by the condition of X to be the Rolewicz space. So that's all, and thank you for the attention.
Thank you for the talk.